Hello everyone and welcome to the 6th video of BIOB20. In this video we're going to see the gamma distribution. For this we'll go back to a previous example about protein evolution. We consider an ancestral protein and a certain amount of time that passes, during which we can have an expected number of 1 mutation, for instance. If we fix the time to a definite amount, we can count the number of mutations that happen during this time, and that is an integer number like 0, 1, 2, 3, etc. And we have seen that this number is well described by a Poisson distribution. The Poisson is a discrete distribution. But another point of view on the same process is to fix the number of mutations and to count the time it takes to obtain this amount of mutations. We can say, for instance, that we're waiting for the time it takes to obtain 1 mutation. And that time can be relatively short, or it can take longer than expected. In this point of view, you obtain a continuous random variable, which by definition has a gamma distribution. So in a very concrete sense, the gamma distribution is a form of dual of the Poisson distribution. Instead of counting the number of events in a certain time, it gives you the time you have to wait until you obtain a certain target number of events. One can sample from the gamma distribution with the function OR_gamma. The first parameter of the function OR_gamma is shape, and that defines the number of events that you have to wait for before stopping the timer. There is also a scale parameter, which is the time it takes on average for one event to occur. We can fix it to one arbitrary time unit, for instance. And as usual, we need to specify the parameter n, which is the size of the random sample, 5 for instance. We obtain 5 random numbers from a continuous distribution. This is very much unlike the Poisson distribution, which takes discrete values. To get some insight into this distribution, we're going to plot the histogram of a random sample. For instance, we will draw 10,000 random numbers from the gamma distribution with shape equals 1 and scale equals 1. We get a distribution that looks very similar to the exponential distribution because in this case, it is actually exactly identical to the exponential distribution. We can make the histogram a little bit smoother by increasing the breaks parameter to get smaller subdivisions. With these parameters, we see that short waiting times are much more likely than long waiting times. Let's see what happens when we increase the number of events before we stop the timer. Let's say, for instance, that we want to wait for 2 events. We can see that the shape of the distribution changes, and this is why this parameter is called shape. In this context, short waiting times are no longer the most likely. Waiting times of 1 or 2 time units are much more likely than extremely short waiting times. If we further increase the number of events that we're waiting for, the shape of the distribution changes again. We can see that the probability of extremely short waiting times becomes very small. Meanwhile, the distribution is shifted to the right, so that the approximate amount of time units you have to wait is 2, 3, or 4. If we increase the waiting time to 10 events, we see that the distribution is further shifted to the right, with an average waiting time of approximately 10 time units. The distribution is vaguely bell-shaped, but it's very much skewed to the right, with a short tail on the left side and a long tail on the right side. And this is because the waiting time cannot be smaller than 0, but there's no upper limit on the amount of time you can wait. This is because if you have to wait for 10 events to occur, then there has to be a minimum amount of time before they all do. But that also stabilizes the average amount of time you have to wait, so we no longer have a distribution that looks like an exponential, but more like a Gaussian. If we now change the parameter scale to 2, we're saying that each event, instead of taking 1 time unit, will take 2 time units. Overall, the distribution has the same shape, but you can see that the values on the x-axis have been shifted. Now the typical waiting time is around 20 time units. So you can see the parameter scale as a change of unit on the x-axis. To recap, the gamma distribution models the waiting time for a target number of events, where we can specify the time it takes on average for one event to occur. Next, we're going to install a library to extend the graphical capabilities of OR. The package is called ggplot2. So as usual, to download packages from the CRAN, we use the command install.packages and between quotes ggplot2. Then I pick the mirror that is in Ontario, the closest to me, for instance, and I press OK. This takes a bit of time and installs additional packages. Then R tells me that there exist precompiled versions for these libraries and asks me whether I want to install the libraries from the sources. I answer no, because this installs the packages faster. Installing the packages takes a little while, but if you don't install them from the sources, then it should run without problem. Once ggplot2 is installed, you can load it with the function library as usual. The command is library ggplot2. We're going to use it to plot the histogram of the gamma distribution. For instance, I create a random sample of size 10,000 from the gamma distribution with shape equals 2. So that's the waiting time for 2 events. And if I don't specify scale, by default it is equal to 1. An important feature of ggplot2 is that the data has to be wrapped up in a data frame. For instance, I can create a variable dat, which is a data frame, where the column variable is the sample that I just defined. Just to see what this looks like, I'm using the function head, which shows that there is indeed a column called variable that contains the numbers from the gamma distribution. Then we create a plot with the function ggplot, not ggplot2, and the first parameter is the data frame that contains the data, in that case dat. Then we specify a variable which is called AES for aesthetics. AES has to say what is x, what is y, etc. So in our case, the value on the x is the column variable. This defines a plot with a particular data, but doesn't say what the plot looks like. For this, we have to specify the kind of plot that we want. And because this is a histogram, we're going to use geom_histogram. This gives us the same histogram as before, but the aesthetics are quite different from the standard plots. We can also see that ggplot2 has issued a warning. This just means that ggplot2 has decided on the size of the subdivisions for the histogram. We can suppress the warning by specifying the value for bins, 35 for instance. That makes a slightly smoother version of the histogram because the default was 30. What's interesting is that ggplot2 has many interesting graphical themes. For instance, we can use the classic theme, which we specify with plus theme_classic, and that changes the outlook of the histogram. This removes the grid in the background and makes the plot overall more empty. As you can see, the general structure of the call is that this is the sum of multiple functions, and each function separates a specific part of the graph. The first specifies which data is being used. The second specifies the type of plot that's being plotted. And the third defines some graphical parameters. There are actually many more available options, and you can keep adding them with the plus notation. Finally, we're going to see how to generate another type of plot with ggplot2. Starting a new session, we need to load ggplot2 again with the function library. Creating some data for the plot, we can say that x is a Gaussian random sample, and y is also a Gaussian random sample correlated with x. 100 data points each is sufficient for this example. Since we're using ggplot2, we need to package them into a data frame. I create a variable dat, which is a data frame, where the column called variable1 is the sample x, and the column variable2 is the sample y. Now to plot a scatter plot of y versus x, we start with ggplot, then we put the data frame where the data is, which is dat, Then we specify the aesthetics, AES, where the variable x is called variable 1 in the data frame, and the variable y is called variable 2. Then we need to specify the type of graph that we want to plot, and for a scatter plot this is geom_point. That already gives a nice looking scatter plot. Again, we can use different graphical themes. For instance, we can use the theme_classic as we did last time. This again removes the grid in the background and makes the plot look more empty. So to recap, the call starts with ggplot, which indicates which data we're going to use for plotting. Then you specify the plot type, and for a scatter plot this is geom_point. And finally you have additional graphical options like the theme_classic in our case. Also pay attention that each element of this call is actually a function, and that we separate them with the plus notation. ggplot2 has many more options, and this is a very popular library to represent data. That's all I wanted to share with you on the 6th video. Good luck with the quiz, and see you at the tutorial.